Hello and welcome to my shop. My name is George and I'm coming to you from Chelsea, Quebec. Now, I already have a woodworking channel on YouTube, but this channel is for some of my secondary hobbies like electronics, programming, and maybe even a little 3D printing. And my projects center around Arduino style microcontrollers. This is the first video in my new channel, and it's about radio frequency transmission. So those really inexpensive RF transmitters that transmit at 433 megahertz in one direction. That's what today's topic is about. Here's a closer look at the transmitter-receiver pair that I'm talking about. Now, I just ordered a lot of 10 of them, and they came in at about $10 Canadian. So these things are going for roughly $1 a piece. Now, the transmitter receivers come in as separate boards, which automatically means that the transmission is one way only, so from transmitter to receiver but not back. So that means you wouldn't be able to set up a telephone with them, but you quite readily could use them for one-way transmission, as in radio-controlled operation of a car or operating a drone visually, anything that just needs one way of communication. Now, there are dozens of videos on YouTube already. They show you simple things like how to wire up the transmitter pair. Others that show you in a little more detail how to use them, how to program them. Just about all of them have you using virtual wire as a library. And with that library, you can use its functions to send strings from one device to another. So text messages, full text messages, can go from one device to another. The way I've done it here in this video is a little bit more primitive. It uses just the raw ability of these things to send pulses, so pulse stream, if you will. And with it you can get control over an appliance or an RC car, and make that thing very responsive to the commands that you're requesting of it. So it's an alternative, and maybe you'll find some use for this way of doing things in one of your projects. So here's an application that exploits the analog properties of this particular unit. So the radio frequency transmission runs from a control box to a mobile cart. And what I've done is I've encoded the different actions as pulse durations. So we have the oscilloscope showing a speed of 1 millisecond per division. So we have 10 milliseconds across the full screen. And there's a pulse that lasts approximately 1 millisecond at the beginning. There's another one that's just off the grid, so the repetition rate is at 100 hertz. Now, the different actions that I want are encoded by different pulse durations. So the cart has a camera sitting at the top, and the camera can be made to tilt forwards or down slowly or continuously. It can be made to tilt up in small steps or continuously. And we can also spin slowly to the right and slowly to the left as well. Then the entire cart can be made to move a little bit more quickly, forward, backwards, and it can spin quickly one way or another for repositioning. Now, I should have drawn attention to this right from the beginning, but during all of these actions, the duration of the pulses on the oscilloscope changed. So different pulse durations encoded these different actions, and so the transmission of the different durations was received by the mobile cart, by the electronics on the mobile cart, and then decoded to run the motors according to what I was asking for. Now maybe you didn't see that happening on the oscilloscope, so feel free to rewind and take another look watching the oscilloscope instead. So this sketch shows you just how simple the connection is to the transmitter and back from the receiver. If you don't count the power and ground, there's one wire connecting the sending logic to the transmitter, and again on the receiving side there's just one wire coming back from the receiver to the circuit that senses the output. And this is basically the circuitry that I used in the next video that shows you how well the sensing circuit follows the pulse duration. What's not in the circuit here, what's not in the diagram, is the potentiometer that was attached to the AT-Tiny 85 that I used on the sending side of things. Okay, so I've laid out the circuit on a breadboard, and I'm showing you the circuit in action on the oscilloscope. So there's an upper trace over here that shows you the sending signal, and a lower trace that's showing you the received signal. So the sent signal is what's coming out of the first AT-Tiny. So it's the signal that's going to the radio frequency transmitter. It's being transmitted over the air. The signal is being received by a second radio frequency device, but this one's a receiver only. The receiver is passing a digital signal over to the second AT-Tiny, and what you're looking at is a copy of that signal. So that radio frequency signal is being detected on one pin, and it's being copied onto a second pin. So when it senses that the signal has gone high, it raises the output, a different output, and when it goes low, it senses that and makes its output signal go low as well. So this is complete processing, if you will, from the very beginning through to the very end. So if you compare the upper and lower traces, you'll notice a couple of things. The first one is that the received signal, the lower one, seems to be longer in duration than the upper one. And if we exaggerate, if we show that difference, so the upper trace is running about 500 milliseconds. I've now got it at 100 milliseconds per division, and the lower one looks like it's going 6 boxes and a half, so 650 microseconds. So that's one thing, is that the received signal is a little bit longer than the sent signal. Another thing that you might notice is that there's an offset, and see there's a delay from the sent signal to the received signal. So let's take a closer look at that as well. And again, I'll increase the time base. So here we're at 25 microseconds per division, and there are three plus divisions to the second signal, to the received signal. So that works out to be about 75 or 80 microseconds delay. Now, the point of this video was to show you how you can get quasi-analog transmission between using just a cheap radio frequency transmitter. So on the first AT-Tiny, have a pot, and that pot controls the duration of the sent signal. I'll start rotating the pot now, and you can see that as the sent signal gets longer and longer, so too does the received signal. We're now out to about 2.5 milliseconds, a little bit more than 2.5 milliseconds, and the following signal. It still has that extra amount of time and that lag, but it's following the sent signal quite faithfully. It's linear, and that's as good as it gets in electronics. So here's the code that ran the demo that you just saw. I'm not talking about the cam cart now, but rather the pulse width tracking that the receiver was doing. Some of this might look a little strange, but it does compile really nicely using the regular Arduino compiler. You don't need a special compiler for this. I'm using some AVR coding, and so for that I include a couple of headers, one for inputs and outputs and one for interrupts. Now if you have any variables that are going to be used in your interrupt service routine, that's what the ISR stands for, you'll need to declare them as volatile. I don't have any variables in the ISR, so this is just a reminder comment, no declarations there. Here's the setup. The first two lines are setting an input to receive the radio frequency data and an output to send a copy of what it's received out to the oscilloscope. I'm using bitwise operators and bit shifting. It doesn't make much difference to use this in a setup, but it does give you faster running code in your loops. So I'm trying to get as much as possible into the habit of doing things this way. So the first couple of lines we dealt with, inputs and outputs declared. The next three are for the interrupt service. So we have one bit that gets set high that says, yeah, interrupts are fine, whatever type they are. The next line specifies that we're open to detecting edges. So either a rise from ground to 5 volts or a drop from 5 volts to ground. Either one of those will trigger an interrupt. And are we listening to any pin in particular? Yeah, we want physical pin 3 to be the source of the interrupt. So if a state changes on that pin, the interrupt service routine will be entered. Here's the interrupt service routine. So it's just a function that gets entered into, in this case, when there's an edge on physical pin 3 of the AT-Tiny 85. So if we find ourselves in the ISR, that means that there has been a change, but we don't know whether it's a rise or a fall. So we test to see if it's a rise. So if the pin is now high, or if the state on the pin is now high, that means that it was a rise. That means that it's, say, the beginning of a pulse. And what I'm having it do is copy that high out to the pin that's going to show it on the oscilloscope. Now otherwise, if the state is not high, then that means it was a low, and that means that the edge was a drop. And in that case, that's the end of the pulse. So set the output pulse low, again using bitwise operators and bit shifting to get it to do what I want. If you were timing the duration of the pulse, then the pulse going high would indicate the start. So this is where you would read the microsecond timer into a variable. And if it wasn't a rise, then it was a fall. So this is where you would read the microsecond timer and subtract from it the value that you had stored when the pulse rose. And that would give you the duration of the pulse in microseconds. Now, it turns out that there was no code needed for the loop, so it's sitting here, but it's empty. So I'm sure I left out something important, so if you have any questions, please just write them in the comments and I'll answer them. So until next time, share your passion.